السلام عليكم ورحمة الله وبركاته. This is me, Muhammad Ghazali Musa, graduate student at Institute Technology Bandung in Indonesia. Uh, I will present a topic about machine learning and turbines energy. So, machine learning is a powerful technique for analyzing, and especially in the business analytics, due to many reasons. We'll discover some of them in this presentation. And turbines is being like a type from the renewable energy or even like a renewable energy that is used to generate energy. And energy is something crucial in our daily life. However, now currently we are seeking for sustainable energy sources. And sustainability is not just about environmental friendliness. No. And beside that, it's also about the viability of the process we are using. So, how machine learning could help us in predicting the energy yield if we change some of the independent factors that are affecting the model? And how about the magnitude of those factors that are affecting the model on itself? So all of them they are different responses among different external factors, and machine learning is included between them. So this is the thing we want to discuss and we want to illustrate in this presentation. Actually, we'll move like through many pillars. We'll give like a some concise and a short introduction to our business issue and the earlier studies that conducted in this topic, the methodology we created, data specification. We'll have bit discussion about the results, and finally we will conclude. We'll conclude this with some recommendations. Actually, yeah, for predicting like the our electrical energy output, it's too crucial for maintaining the efficiency and also for maintaining the sustainability of the process we use. In our case, we are dealing with confined cycle power plant, as we know that like some small changes in ambient conditions, like ambient temperature, ambient pressure, they could change and affect the power output. And after that, it will affect the economic yield, which we are seeking for in the most. So accurate and efficient predictions, they are like necessary needed, like, to optimize the plan's performance in order, like, to find the maximum possible power output under various operating conditions. So this important, like, is expanding the global interest of renewable electrical energy, and it's too crucial for the energy sector. As now currently we are looking for different sources. So here like maybe like schematic infographic about like the combined cycle power plant. So the combined cycle power plant, as we are seeing here, it contains different compounds, and all those compounds they have such an impact to the final energy yield of it. And even more also about the emissions of carbon dioxide and nitrogen oxides. So, okay, how those factors are affecting the final energy yield, this is the thing that we want to aim when addressed through machine learning. So, okay, this is machine learning. So machine learning is like actually, it is one of the most useful like tools, okay, in order to determine the relationship between the input and the output. For our example, so the input variables are the ambient temperature, pressure, humidity, and also we're talking about vacuum. And for the output is the energy yield. So we are having like different problems, and some of the problems they are linear. It means they have like a direct relation between the output and the inputs. But in the most, we are in stochastic system this life. So not all phenomena could be interpreted with a linear model. So complexity, nonlinearity always exist. So machine learning could handle this very well about finding a relation that manage the output and the input, manage the independent variable and the dependent variable. So we have a lot of things, those things that are affecting the energy yield. So we are trying just like, to find a good pattern that could be given as a model for this phenomena or for this case. So different studies have been conducted about this topic. So maybe, for example, let's consider the first. So it considered four variables: ambient temperature, atmospheric pressure, relative humidity, and also exhaust volume in order to determine the electrical output. But in this case, it just gives artificial neural network as it's one of the most popular machine learning algorithms. And actually, it's deep learning in the machine learning. He used data size around 9,500. Following, some other research also use the same data set, which is compiled like 9,500, for determining the same output. But the differences they were in the method they used, the machine learning, because machine learning contains different models. And model to model, they are different also in their responses and their like performance. So they studied their performances. But for example, the second study studied about the super ensemble learner, which is as a base learner combining like many things, are a support vector regressor, nearest neighbors, decision tree, gradient boosting, extreme gradient boosting, and some other research. They already also studied about the multiple regression, the neighborhood. Some studied about the transparent open box, and some also like extremely randomized trees. So concluding from here, this is one of the hottest topic because many research still are being doing like regarding determine the power plant output. Like so the other thing. In our case, for this, I used data that collected from the same purpose, but in different time span. From 2011 to 2015 means 4 years. So among different sensors to measure different things, ambient temperature, also ambient pressure, and many things that we will illustrate about them soon. So the dataset is around 36,000. And in this study, I used different machine learning models to know about the variety for using them. The first one is linear regression, support vector regressor, which is always used, but in a different data set, serving the same purpose, yeah, of course. Also light gradient boosting machine learning regressor and gradient boosting regressor, extreme gradient boosting regressors. So, in general, I want to predict the energy yield, or here TEY, which is a total energy yield, by using like 6 machine learning models, which are some normal, like as support vector machine, and also like for linear regression model, which they use like as a baseline, just like to determine the efficiency of others based on them. And we have also about data set. This data set is being divided and split to two, like training set and testing set. And the measure performance or the measure metrics is about root mean square error and the mean absolute error. Due to many reasons, we'll discuss about them. So the best model in the term of root mean square error and mean absolute error will be chosen to represent this case. And in the end, there is something called Shapley explanation analysis in order to determine what are those factors that are affecting the model in a most. So, five files among those years have been compiled together in a one file to create the overall data about the gas turbine factors. So, this data is being split to training and testing sets. And after that, it inserted to the machine learning models, those six models. And we use tenfold cross validation. We validated them. And after that, the output is being measured through those matrices. Root mean square error in absolute error. And R square here we use in just like to know about the model adequacy for handling this or for handling the variance or for showing the variance among the data in itself. And surprisingly later we'll discover that those R scores are almost very high, which will show about the significance of the model in handling those variances among the data very well. So, in overall, we could say like this. Sorry. So, the core about machine learning or about the predictive method, because machine learning is predictive tool, but it serves different purposes, regression, or maybe it serves also classification. It depends on the method we want to use. Also, like many different like deep learning algorithms, and also like when you talk about reinforcement learning, so many things. But here we want to predict in order to see the unseen pattern. Okay, because like normally how we could like relate those data sets to each, it's through combining them as like through different models. So machine learning is taking those data, okay, and give a clear pattern for them based on different or many things. So those algorithms, their primary goal is about to maximize accuracy on the unseen data. As now we know about like the labels, the targets, as I have like different around nine independent variables, okay, and I have just the energy yield as the dependent variable. So I know about this dependent variable, but later, how if I change those independent variables? So what is the output? I don't need like to move to that stage and after that decide which output I need to change, and after that I need to observe the output in order to give a conclusion about my stage. Like for example, uh, ambient temperature and also ambient pressure, they're affecting the model. But how they are like affecting the model if they change. Okay, now the ambient temperature is 30 degree. So how if you change that? Or if you change it like to 40, for example, due to different factors, natural or also synthetic one. Okay, how it is like affecting the model? Yeah, it's unclear without having like a statistical relationship. So the thing is like this, we need to perform predictions in order to assess the future viability of the thing. So the main aim about the prediction is to maximize the accuracy on unseen data. Many uncertainties, and we are in a stochastic system. So many things could happen. But at the end, we have a data currently. Through this data, we could extract some feature, extract pattern that compile them together in order to give our insights about the future change, what will be. So we have two things about machine learning. It could be predictive and it could be also descriptive toolbox. So in descriptive, we want to understand and qualify the relationship between those variables. And moreover, the key questions we need to ask ourselves about the prediction aim and also the interference aim or the inference aim. is what will happen here. Okay, for the inverse EM or for the discrete EM, what does it happen or how does X affect Y? So we're talking here about the magnitude, or how about if I change it, what will happen? And there, what will happen in a term of okay, I have those input variables and I have one out variable. So how if I change those, what will happen? But how it will happen? So there are different purposes actually. So for the model type in a prediction way, it's complex. It's something called like, let's say black box, deep neural network, or we are using like ensemble models, basic linear regression model. But I'm going to talk about like simpler linear logistic regression in order to describe the data and describe the relation between those data to each, like the features, how they are related to each. Yeah, it's descriptive. So the focus in the prediction aim is about the output. Why we have many axes, many features, but we are focusing about the response at the end. How it could be depends on the target we set for optimization, as we are minimizing something or optimizing something. Here we want to optimize the energy of. So we are looking for the factors that significantly affecting the model in order to be maximized. And also about the internal parameters, the coefficient and structures, they are showing us about, or they are describing the magnitude of those independent factors. So we are using the prediction models in a most for automation, forecasting, classification task, while the descriptive ones for business intelligence, for policy making, and also for scientific discoveries. So here are the main six models we use in this case. We will break down them typical to their principle, typical to their interpretability, performance, training speed, and also some feature scaling, and we'll see about like how they could handle nonlinearity well and their typical use case. So actually, we need in everything in order to qualify, we need a baseline. So for this reason, we choose linear regression as a baseline for our model building or for our model performances measures in order to choose like the upper model. So yeah, linear regression from its name, it's linear, is putting a linear relationship between the inputs and the final output. So it's used in many tasks, and it's the most simplest one to be established, to be described, too fast, which is scalings. Yeah, it doesn't need like that much of focus in feature scaling, etc. But the problem about the linear regression is it's not handling the nonlinearity. So it means it's not handling the complex situations, right? So for this reason, we need different models or different algorithms to handle this nonlinearity. So choose support vector machine in order to do it. Gradient boosting, extreme gradient boosting, light gradient boosting. Those are ensemble models. Many of the research they stated about the importance and the high performance of those ensemble models in serving the matter of nonlinearity, the complexity of the systems. So right, the first thing, okay, we have maybe the in a term of like interpretability, yeah, support vector regression is low, gradient boosting low, low, low. About the performances, most of them they are high, especially extreme gradient boosting and light gradient boosting, which they are different in terms of computational power. And also about the training speed. Yeah, light is very almost light, it's like very fast. Yeah. So those are the main differences. Here is the conceptual way is empirical explanation. But how about in the actual scenario? How they could be present our model or our data? This is the main question we are aiming to solve or to answer. So yeah, performance metrics, in order to assess their prediction capability, we need to have like such performance matrices. So here we use mean absolute error, which is a straightforward measure, as it's just generally having the mean of the difference between the predicted and the actual value. We need to minimize it. Okay. Even so, also for the root mean square error, it's just like about squaring or about having like a square root for the square of the error, which is the difference between the actual and the predicted value. So later is too sensitive for the large errors, as if we have a very big difference, maybe let's say 10, and the others like around scattered between 1, 2, 1, 2, like this. So it would be too big, yeah, because it's sensitive to outliers. This is a problem. And coefficient of variation R square is employed to show the variation in the data that captured the model in all overall. So yeah, let's break down the data. So we have like, many features: ambient temperature, ambient pressure, humidity, air filter difference pressure, gas turbine exhaust pressure, inlet, outlet temperatures. We have discharge pressure. We have carbon monoxide, and also nitrogen oxides emissions. Those are independent variables, while the last one, the turbine energy yield or the total energy yield in an hour, is the dependent variable. So here we are. Firstly, we need like, to have like the relationship between the data, between the input and the output, or even between the all data in the mass manner. So to find this one, we need like Pearson correlation matrix. What is it? It's like matrix or a visualization tool. It's just like giving interpretation about how the state like or how those features are related to each. It's given by the coefficient or like what's called the correlation coefficient R. So the correlation coefficient is representing like this. We have a strong and we have weak. So the strongest relationship or the strongest, we have a strong and we have weak, and we have a strong positive and a strong negative, weak positive, weak negative. So the thing is like this, when it be like one, it means we have a strong positive relationship. When it be zero, we don't have like, any relation that could be figured. And this is a good because we are always seeking about the independency. We don't want like those features in the model be dependent on each, right? And similarly, for the negative value, -1 is the largest or the strongest negative relationship. So as we are seeing here, for the ambient temperature, it has almost zero with a year. So it doesn't like relate to year. But we have some of the factors that are related or they are correlated intensely to each, as TIT, GTEB. They have around almost like a strong positive relationship approaching 0.9. Also, 0.96 between the energy yield and GTEB, which is also very significant. And similar like this, because we want to study the whole aspect, so we didn't remove any data from those data sets to know about how the baseline of the model without changing anything. And after that, the enhancement of the model will be later. Okay, so here we'll have like some results. Actually, after inserting the data, after dividing them to training and testing sets, and with 10 cross validations. So we already obtained those responses. As we are seeing here, support vector machine the words. Even for R square, it's not showing the variance between data very well. It's just like about 0.3. And also it's giving around 12 root mean square error, which is very high because we are talking about megawatt hour. But for other ensemble models, they show very well, additional to linear model also, if you compare to support vector machine. So yeah, here the best model describing the data we gave is extreme gradient boosting, showing about 0.9985. But the most matrices or the mud matrices we concern about them is the mean absolute error and a root mean square error. So for the mean root square error, it achieved the minimum. While for the mean absolute error, yeah, it's kind of not the minimum. The minimum is like yeah, the difference about 0.02, but we consider the priority for the root mean square error because like even it's sensitive for the outliers. So yeah, and overall, we already chose extreme gradient boosting machine learning algorithm. So for optimize the model, we need to adjust or to set some parameters. It's about optimization set in order to give more optimized response. Like we have something called hyperparameter tuning, which is like the process of selecting the optimal settings for a machine learning model to achieve the best performance. Here we are trying, to measure the power plant energy output in the most accurate way through the matrices we use in order to measure the difference between the predicted volume and the actual volume, later to be viable for prediction and extrapolation based on the inputs we insert, typical to the inputs or typical to the same features we already trained the model with, right? So and overall, we choose four values for each: estimators, learning rate, maximum depth, subsamples, and those valid is yellow. They are the optimized values. So overall, we use Python for doing those tasks. So we are clearly noticing here how the model is different after optimizing the hyperparameters. Okay, for example, for the root mean square error, it decreased to be 0.5 from 0.61. Even so, for the mean absolute error from 0.44 to 0.37 megawatt hour, which is considerably high. And further enhancement could be made if we are looking in a wide search area. If we optimizing the model or optimizing or turning like the hyperparameter small. It's like this. Right. So here is a Shapley analysis. It's showing that the first, second, and the third that are the most impacting the model. Ambient temperature and also turbine inlet temperature and even about the compressor discharge pressure. Right? So we could not leave those. Like there is something called feature engineering. So in a feature engineering, we are using the most significant feature in order like to save the model or to optimize the model because some of them they are just like giving penalties to the model. So clearly here the machine learning give explanation, it's give prediction, compile all of them together, which is making it one of the most powerful tools currently or at the meantime. So here the model fitting for the test set. So after we already train a model, turn it or turn it like the hyperparameters. This is the last output. As we are here, we have the perfect relation between the actual value and the GQ value, and they are most scattered around this straight line, which is showing significance and showing the high performance of the model we use. So in overall, here we are ending um, the conclusion and recommendations are like this. Among the models evaluated, extreme grid and burst algorithm deliver the best performance for predicting energy. Subsequent hyperparameter tuning further improve the model, reducing the root mean square error from zero point 0.6 to 0.5 and the needed absolute error from 0.44 to 0.37 megawatt per hour, which is considered very good. Further enhancement, it should be made. What we do about feature engineering, about rigorous hyperparameter tuning, and maybe more also for the model. We could also try other models for machine learning. And after that, just screen and take the best. So yeah, here are some of the references I use for making this presentation. Thank you very much for watching. Assalamu alaikum wa rahmatullah wa barakatuh.